Today we're going to go over, the first thing that we're going to talk about is who likes to form what in the terms of ions. Then I'm going to go over a special stability case for the electron configurations, which is pretty important. So you definitely want to have your periodic table out as well. All right, let's start off with discussing forming ions. In general, when we're talking about the formation of an ion, before we go there, what is an ion? An atom with a charge. Good. So how does an atom get a charge? Very good. So you gain or you lose an electron. And generally speaking, metals lose electrons, and nonmetals will gain them. Now, when you look on your periodic table, the majority of the periodic table is what? Metals. So we got a lot of metals over here and a very small amount of nonmetals over here. And metals are trying to give away their electrons, and the main reason is when we talk about valence electrons are contributed to the s and the p orbitals. And when we look at the metals, they really only have, the majority of the metals only have s orbital electrons, where some of them are starting to get some p orbitals, and then as we get farther down, there's some D's and F's, and so it gets a little wishy-washy. However, the metals only have 2 valence electrons, and so they're either trying to gain 6 more electrons to fill up the outermost s and p orbital, or they're trying to get rid of those 2. And let me tell you, it's a lot easier to get rid of 2 than to gain 6 more. However, if you look at the nonmetals, as we move across the periodic table in this direction, we start to fill up those s and p orbitals. So right around here in the column 5, 6, and 7, they're just a couple away from having an octet or 8 total electrons. So these elements want to gain the electrons. So generally speaking, again, metals will lose, nonmetals will gain. So what will the charge on metals be if they lose electrons? Positive, and nonmetals will be negative. Good. Metallic properties, this will have a lot more importance when we start writing chemical formulas, which isn't anytime soon, unfortunately. The representative elements, again, are those elements that are in the first 2 columns and last 6. So we do have, those are the types of elements that we're going to be focusing on most when we talk about the charges. These guys, they act a little bizarre, so we're not going to focus on them just yet. However, if we look at the metals here, they're going to lose, the nonmetals are going to gain. Now, this last column on the far right, what are those? Noble gases. And how many valence electrons do they need to gain or lose to get a full octet? 0. They're full. So when we talk about noble gases, they're very unreactive because, 1, they really don't care about any other element because they have their octets. They don't need anybody to either give the electrons to or to take the electrons away from. Everybody else is trying to get to that same configuration that a noble gas has, or at least the nearest noble gas. All right, go ahead and get the blanks here, and then I'm going to turn the lights on. There is, and you can write the special stability rules in this area right here that I'm going to write on the board, but go ahead and get the blanks. Looks like we got stability. I don't see any more. Oh, electrons. Man, I hate colds. I'm just snotting away like crazy. So stability and electrons are the 2 things there. All right. In that open area in your notes, I want you to write this down. And again, I don't remember if I put this in the notes. I doubt it. If you can have a half-filled s orbital to get a half-filled d orbital, we'll do that. Okay. If you can get a half-filled s to get a half-filled d orbital, we'll do that. Or, and there's 4 exceptions here, to get a half-filled, spell right, half-filled, not filed, half-filled s to get a full d, we'll also do that. Or we could have a empty S to get a half filled D. We'll try that. And the last scenario is empty out the S's to get a full D. Now you're sitting here going, what the heck is he talking about? It's a good question. Okay. When we look at the periodic table and we're looking at the transition, you have it written down, so I'm going to erase it. All right, let's take a look at, and you have your periodic table out. Let's say that I'm looking at, I don't know, chromium. Chromium. Yeah. And I'll go ahead and write the shorthand notation, actually a modified shorthand notation / arrows or diagram. Okay. So the last noble gas before that is argon, just to speed things up. So chromium is in which row? Fourth? Is that right? Okay, so we got the 4s, and we're going to have 1 electron there. And then in the 3ds, 3, 4, 5, chromium has, what, 4? Yeah. Okay. And this is how I taught you, and this is fine to get you going. We can always, and I notice how I like that, slopes downward. According to the 4 stability rules, I can take an electron from a higher energy level and place it in a lower energy level. Now remember from our writing the electron configurations that the S's have the lowest energy for our orbitals, and the F's have the highest energy. Okay. So what we can't do is we don't want to write 4s, 4d, 4p, because then that would say that D has lower energy than P. So that's why we do the 4s, 3d. Now, since we have a higher energy orbital here with an electron in it, remember the story about sharing bedrooms? Yeah. Well, in this case, we don't really need to share the bedroom. We can take this higher energy electron out of that orbital and place it in a lower energy level orbital so that everybody has their own room. And crazy enough, that's what happens. Okay. So in this case here, I have the first scenario where I have a half-filled S, because I took one of the higher energy electrons out of that orbital and placed it in a lower energy 3D. Okay. So I have a half-filled S and a half-filled D. Okay. Now here's the bad news. This rule, or this special set of cases, only applies to the first 2 rows in the Ds. So the 3Ds and the 4Ds. So it only applies to those elements in the 3D and 4Ds. Why would it not apply to the 5D or 6D? I'll give you a hint.
Too high of an energy?
Well,
because of those 2.
The F orbitals, very good. So the F orbitals actually are lower than the higher energy P or S's here.
Yes.
Okay, so these guys don't get to take electrons from the F's, or F's don't get to give them over to the D. Okay, so there's no set. You're never gonna have to worry about, oh, let's make sure everybody gets 1 and then we'll fill up half and half. No, that doesn't work. Okay, so it only applies to the first 2 rows within the D's. So some elements in 3D and 4D. Let me give you another example. Everybody good with that one? Let's say that we're looking at not chromium, but who's another good candidate? Let's go with good old copper. Let's go with copper. Yeah. Okay, so copper, the way that we did it before, looks like this. Okay? That's how I taught you the last couple days, and I knew that I was going to teach you this half rule, or the special stability. What can we do here? Or will it work? Now, here's another thing. Some elements, and I'll give you some examples, can't use these special stabilities. It only applies to those that can move 1 or 2 electrons out of the s orbital to make it a half filled, or a half filled, or a half and a full, or an empty and a half, or an empty and a full. I just went down those 4 lists there. So is it possible to have special stabilities with copper when it's neutral? Yeah, we'll take one of the electrons out of the 4s and fill it up in the 3d. Okay. Now, some of you might think, well, that's weird. Why in the world would we take an electron out of the 4s and double up everybody in the 3d? Well, that's a simple answer. When you become a senior, do you have special rights in this high school?
Yeah.
Yeah, you have to be in the LC. This is the senior class. These are the freshmen. They have to bunk up and double up. Seniors sleep alone.
Oh, sadness.
Okay. So think of it like that. All right. Let me give you another scenario. Let's throw iron in the mix. Fe, good. And go ahead and rewrite all these guys.
Kira has a question.
Yeah.
Alright, so how come you're not moving from the S to the P?
Ah, good. The reason why we're not moving from the S to the P is because number one, we don't have any electrons in the P's, and the 4P would actually be a higher energy level than this. So we can't take electrons from the D and put it in a higher energy level without exciting the electron or the atom.
Okay.
So we'll never move electrons from here to here, but we can go from here to here because it's a lower energy level.
Okay.
Yeah, Kelsey.
I'm like, how do you know if you can use this free element or if you can't?
Okay, I'm going to give you an example right now. And you're talking about the special rule. Okay, here's iron. Here's iron. Okay, and this is the way that I taught you this before. Okay. Now, can one of the 4 sets of criteria be met here? In other words, if I take one electron out of the 4s and place it in the 3d, will I have a half-filled d?
Nope.
No. If I take both the electrons out and put them both in the 3d, can I have a full? No. So this is it. We're done. If it can't be half, half and half, or half and full, or empty and half, or empty and full, don't do it. You gotta leave it alone. Okay. Yeah.
Does half mean like 3?
Half means however many we would normally have. So how many can the S's have?
Okay.
2. So half would be half of that, which would be 1. And then the D's can have a total of how many? 10. So it'd be 5 or 10. And that's to get to this, or this, this, or this, this, or that, or this, or that. So that's what we're shooting for right there. Now again, if we can't force it. We can't go, okay, well, I'm going to get creative here, and I'm going to take an orbital or an electron out of the 3 P's and pop it in there. No, now you're just messing everybody up. And you're taking it from the core. So now you're starting to really get personal when you take it from the core. All right, let me give you one more example here. And we'll have fun things like this on the quiz, of course. All right, let's go with NB, not one of your favorites. So here is how it looks. Can we do anything with that?
No.
Not one of your 52, so don't freak out.
Yep, you sure can.
We can? What do we need to do?
Empty to a half.
Say it, John.
Empty to half.
Empty the what?
Empty the S.
Oh, S. Okay.
Say empty the half.
That's what I thought I heard too. And then put them over here?
Yep.
Yeah, there you go. Yeah, Julia, go ahead.
I thought it could only be to the 3D and 4. Just kidding.
Gotcha. Got it. Okay. And again, if it won't work, don't force it. So that's what this is talking about. Also, one thing that we're not going to do in Honors Chem, but we will talk about in AP, is the special stabilities when we have ions. Okay, so I won't do that to you in here. But at least you have it in your notes for when you get there. Sevens are part of your homework, and let's make sure that I don't have any crazy questions in there. Periodic trends. Now, periodic trends historically are always a class favorite, and I'm being very sarcastic when I say that. I don't know why, but again, when it comes down to students wanting to know why something is the way that it is, they really don't care. They just want to know, tell me the answer. Okay. Well, here's the reason why in some cases, so bear in mind here. And we're going to talk about the trends. We're going to talk about radius. We're going to talk about ionic radius. What is radius again?
Like half the distance.
Yeah, okay. Or if we put both of those radius together, we make a diameter. So we're going to talk about how big atoms are today, for the most part. And then we'll talk about what affects their size with how many electrons are present. All right. Generally speaking, and again, generally speaking, the radius of an atom decreases as you go from the left to the right. Okay? Along a row. So once we hit a row and we're going from left to right, the radius gets smaller. And here's the reason why. If we look at, and I'm looking at the graphic, I don't know what page it's on, but as we look at the graphic here, how many valence electrons does lithium have? How many valence electrons? That might be a good quiz question. How many valence electrons does lithium? 1, because it's in group 1A. And again, valence electrons are the outermost s and p orbital electrons. Better said, it's the number of s and p electrons within that same row that the element's in. So lithium is the first element in that row, so it only has 1 valence electron. Now, everybody's either trying to get to 8 valence electrons or 0 valence electrons. So if I know ahead of time, and again, these are thinking atoms here, if I know that I need to either get to lose 1 electron or gain 7 more, what's going to be easier? Lose 1. So what lithium's doing is it's teasing the other atoms. It's just hanging that electron out there. It's like, here you go. Who wants it? Okay. And the reason why is because it's so big that it only has 1 electron in that outermost energy level. So it's just teasing everybody. Like, here, take it. Okay. But as we move from left to right along the periodic table, we start to get, we start to fill up those s and p orbital electrons, and they become more possessive. In other words, and some of you may know this or may not know this, but as you get more and more money, you don't want to spend it anymore. That's being smart with your money. All right? As kids, we don't have any idea what that means. So we get money, we burn it. Okay? We go and spend it. Keeping the economy alive. New iPhone comes out here soon, so let's go buy it. Exactly.
Saying that children keep the economy alive.
Yes, they do. All right, so as we move left to right along the along the periodic table, they start to get more and more of those s and p orbital electrons, and they become more and more possessive, and they get greedy, and they're like, you're not touching it. So the nonmetals over here, they're fighting to hang on to those electrons because they know they're almost to the goal, and that is 8. Okay? So generally speaking, as you go left to right along the periodic table, the radius gets smaller. Now there's a few hiccups, a few bumps. I don't see it on this row. But as we get farther along the periodic table, there are a few times that it actually gets a tiny bit bigger. I can't see it right at the moment. Oh, well, don't worry about it. Oh, there it is, 40 to 42. See, I knew there was 1. All right, generally speaking, as we go down a column, what happens to the radius? It gets bigger. Now, why?
Is there more stuff in the atom?
Well, not in the atom, but around the atom, which are what? Electrons, yeah. And it's all about the electrons. How many electrons you have determines how big or small you are. Yummy. All right, so as we move down the group, I'm going to die in front of everybody.
What is wrong with you? Stop.
That'll be edited out. I'm trying to keep Jake awake here. All right. All right. So as we move down the group, we're filling up energy levels with these electrons. And the more electrons you have, the bigger you are. Okay? So, just that simple. Or actually, the more, yeah. Now, ionic. Oh, yeah. Let me talk about shielding and effective nuclear charge real quickly. Now, listen up. Hang on. All right. I'm not too worried about you knowing what shielding and effective nuclear charge is in honors. It's nice if you have a slight idea. But let's talk about effective nuclear charge and shielding. They actually do associate with themselves here in the same way. If I'm looking at the nucleus, don't do that. If I look at the nucleus, what's the charge on the nucleus?
Neutral.
Positive.
Yes, it has protons and some neutrally charged neutrons. Okay. However, for the most part, it's positive. And then if I look at electrons, they have what charge?
Negative.
Negative. And if we have these layers or orbitals of electrons, let's say I'm an electron way out here, and there's a whole bunch of other layers or levels of electrons that are blocking this positive charge. So we got all these negative charges, and then I'm this electron out here. How much of an influence is that positive charge on the nucleus going to affect me as a far out electron?
Not very much.
Not very much, and that's what the shielding is talking about. That as we get more and more electrons, the ability to, quote unquote, be attracted to that positive charge gets less and less, which also causes the atom to get bigger, which also causes these electrons to get taken without anybody knowing it, okay? Which in some cases is not bad. So when we talk about shielding and effective nuclear charge, we're talking about the negative charges between the electron and the positive charge on the nucleus, which probably doesn't make any sense right now, but hey. All right. Ionic size. Again, what's an ion? Good. So charge. Either it gains electrons or it loses electrons. Now, there is no trend on your periodic table. It just deals with a particular atom. So hydrogen atoms can either be positive, it can lose one electron, or it can be negative, it can gain one electron. It can also be neutral. So the general trend is as you lose electrons, you get smaller. Okay? Think about it. If I'm looking at lithium, how many protons does lithium have? 3. Very good. So originally, when it's neutral, it has 3 electrons. If I take one of those electrons away, do I have more positive charge or more negative charge? Positive. So that means I have a much stronger influence from the nucleus drawing these other 2 electrons in. So it draws them in closer. And besides, the only electrons remaining for lithium are the core electrons. So now it's really fighting to hang on. It's willing to give the 1 away, but it's not willing to give 2 away. All right. On the opposite end of the spectrum, if we look at the nonmetals, they're trying to gain electrons to get that octet. And if you look at, say, oxygen, when it has a -2 charge, these are in picometers, 140. When it was neutral, oxygen was itty-bitty 73. 2 more electrons and it doubles in size. Yeah. Why? Well, the main reason is because it has more negative charges than positive charges within the nucleus. So the nucleus can't really hang on to those. Besides, when it gets these other electrons, it relaxes. It's like eating a nice Thanksgiving dinner. Your belly's full, you relax. And that's what's happening with these guys. These guys are tense. They're like, I just gave away some electrons. I can't give away anymore. These guys are loaded. Like, thanks. Hey, no problem. Okay? So generally speaking, as you become more positive, you get smaller. As you become more negative, you get bigger. And don't ever use the periodic table to go, oh yeah, as you go left. No, don't do it. Can't do it the same way. All right, ionization energy. What do you think ionization energy deals with?
Ions.
Yeah, it deals with ions. Actually, the amount of energy needed to remove an electron. Okay. Ionization energy deals with the amount of energy needed to remove an electron. Okay. We won't ever have any energy to add any electrons. It's always to remove. And again, what do metals want to do? Do they want to give away their electrons or take on the electrons? Give them away. So it's not real hard if I'm hanging this electron out and say some non-metal wants to take it. Okay, it's not going to take a whole lot of energy. However, as we move farther to the right, good luck trying to take any electrons away. It's not going to happen. So those ionization energies increase as you go from left to right. However, they're not gonna give them away. They will if you put up a big fight. Okay? So generally speaking, the ionization energies increase as you go from left to right along a row. Because again, we're moving from metals to nonmetals. And nonmetals aren't a big fan of giving away electrons. They're a big fan of taking electrons. A little bit later on, we'll talk when we start doing chemical bonding, especially with ionic bonding. I associate the metals with the males, my own personal experience. In other words, they're giving away their electrons left and right. Who's taking them? The nonmetals. Who are the women? Okay? And that's fine. You just don't realize that men really like giving it away. So, and you guys like taking it. It's all right. We got this nice symbiotic relationship. It's good. All right, here is a diagram, and I hope you have it in your notes. I think you do. You'll notice that the noble gases, there are big advocates for fighting for keeping on those electrons. Helium is the largest. It's like, you are not going to take this electron. Where lithium's like, yeah, here you go. So lithium wants to give away that electron. Helium's like, you're not even, no.
I don't like you that much.
Exactly. Now, there are a few hiccups here. Notice how it goes from helium down to lithium, which we'd expect. However, as we go from lithium to beryllium, taking those two electrons, yeah, it increases, again, as you go left or right. But why do you think it bumps down from beryllium to boron? And then it goes up, up, down, up, up, down. And then down, right. So why is there that hiccup? It goes 2, and then 3, and then 3 more.
It's a pattern.
Okay, it's a pattern. But what do these electrons, where are they at? S orbitals, right? So we fill up the s orbital. As soon as the s orbital gets full, it's kind of like, I don't really want to leave. I got my friend here. But as we come down to the first p orbital, taking that one away is a little bit easier than taking the second electron out of the s, which is weird, but it's okay. So we start dropping electrons into each of the p's, and then it's like we double up, and it's like, get him out of my room. Okay, that's what oxygen's saying with that bump down. It wants its own room back. Okay, and then increases as we add the 3 more. Okay, you're not going to be tested over this, just the general trend. And what I want you to know is, as you go from left to right along the periodic table, the ionization energies increase, generally speaking. Okay. And then I just talked about the deviation of the trend, and that's because we're dropping electrons into the p orbitals, then we're doubling up on the p's. Once s is full, it's a little more possessive. Okay. All right. Everybody had the blanks on that one? There's 2 of them there. What do you think happens to the ionization energies as you go down a group or a column? Yeah. Why do you think it decreases as we go down? The atoms are getting bigger. So it gets easier to remove that electron. As that electron gets farther away, that you're trying to take away, as that electron gets farther and farther away from the nucleus, that effective nuclear charge that it's experiencing on the nucleus is much, much less. So if you've got a really big atom, that first ionization energy isn't going to be very large. Now, for the most part, noble gases don't form compounds until you get down here. Then we got the big boys. They just don't realize, oh yeah, there's an atom over there. Oh hey, how you doing? Okay, so we can form some compounds here. They just don't realize that chlorine and fluorine are attaching themselves there. Okay. All right. This diagram here, or this table here, shows the ionization energies as we try to remove each successive electron. That's what IE1 stands for, ionization energy for the removal of the first electron, ionization energy for the removal of the second electron, so on and so forth. The goldish area, I think that's gold, yellow, brown, whatever that is. This represents trying to remove electrons from the core. Again, it's not impossible, it's just going to take a lot of effort. And notice that it's a little over a 400% jump. That's my rule of thumb. If it's a jump of over 400%, then you're pulling from the core. Alright. So, sodium, group 1A, here's the one electron, take it away. You start taking away the other ones, now it's putting up a fight. It's not going to be happy. Same thing with the other elements along the row there. And I'll give you an example here in a moment. And I put on here 9 times greater, but really 4 times greater. We're almost done, aren't we?
Yeah.
Okay. So close. And then, so 9 times and removes. And then this table here is nice in that it summarizes all the trends that we just spoke about. So the atomic number, yeah, we talked about that earlier. The atomic radius decreases, ionization energies increase, metallic properties, which will have a little more importance once we start writing compounds. But again, as we move in this direction, we're heading toward the nonmetals. As we go down, it becomes more metallic. And that's really important because when we start writing compounds with like 2 nonmetals, we always write the metal first. We'll talk about that later. Okay. So the 8s are part of your homework. And I do want to give you another practice problem that's not on here. Kind of bummed that's not. So let me turn the lights on. Because they're on the test, that's why I want to ask you this. Not on the quiz, but on the test. What's that?
When's the test?
Friday.
Test will be next week.
Next Friday?
Depends on the class. It's like a Thursday-Friday combo.
You
So
and
for you
Friday-
guys, it sounds like Thursday.
You and Friday tested.
Here's a set of data. We got IE1, IE2, IE3, IE4. And we'll say that we've got 333, 795, 6,422, 7,388. And these are all in kilojoules per mole. Okay, you don't know what a mole is, so I forget I said that. Here's my question. Here's ionization energies for a single element. I want you to identify what the element is. And don't look on your table because I made these values up. Okay. So, sodium, barium, aluminium, or carbon. Okay. Let's do that. Okay, so you got sodium, barium, aluminum, and carbon. I've got ionization energies, 4 sets of ionization energies. Who does this represent for? And you're all looking at me like, what the crap is he talking about? Yeah, John?
Carbon.
Carbon. All right, well, let's take a look and see if you're right. If we go from here to here, is this an increase of over 400%?
Yes.
Wow, you guys.
No?
Not really.
No. Might be a little over twice.
Yeah.
Good job. Okay. How about we go from here to here? Is that an increase of over 400%?
Yeah.
Yeah. All right, so here's what we're saying. The first electron is easy to remove. Okay? And we're looking for the jump in between. So between here and here, that's over 400%. So what this is saying is, removal of the first electron is somewhat easy. Removal of the second electron is somewhat easy. And again, remember, as we go left or right, the ionization energies are going to increase. So the removal of that third electron is difficult. Actually, we're starting to pull from the core at this point. So knowing that 2 electrons are easy to remove and pulling the third one comes from the core, what group are we looking at? Group 1A, 2A, 3A, or 4A? Again, 2 are easy, the third one is difficult to remove. 2? Who's saying 2? Why? Go ahead, Savannah. You're pulling from the core. Good. Now, here's what I want you to do. Look at your periodic table. look in the top right-hand part of the box there. You got a number. What do all of those elements in group 2A, what number do they have there? 2. Means a positive 2. Means that when those elements become ions, they lose 2 electrons. So the answer is barium. 2 electrons are easy to remove. The third one is up here in the core. Okay? So you have to ask yourself, how many are easy to remove? That tells you what group the element's in. Okay? So how many are easy? Yeah, Julie.
How do you know that the third one's hard to remove? 'Cause it's like
The big jump of over 400%. So if you need to have your calculator out and you go, oh, that's about 9 times greater, or 900%. Let me give you another one.
Okay.
Bye-bye.
It's on the video. Okay. And your options are okay. Who does this set of ionization energies represent for? Indium? Okay. Well, let me ask you this. Where's the big jump take place? Between the first and the second, right? So the big jump occurs right here. So that means the first electron is easy to remove. All the others are hard. Lithium.
Can you say that again? I didn't got this.
Are you going to listen now? Awesome. Here we go. All right. So we want to look at the values. And again, they're not the ones that I have on the sheet of paper. But if you have a large jump or a large increase in energy, what that means is you're no longer pulling valence electrons. You're now pulling from the core. So wherever you have your large jump, and I'll tell you, the first electron's always going to be easy to remove. Okay? So you just have to find where the big jump takes place. Is it between these two, or these two? So this one's easy to remove. Now, if I try to remove this one, I'm pulling from the core. And if I pull from the core, that means that I can take one easily. Everybody else is hard or difficult. You want to do one more? Okay. Which element?
Second one.
Third one.
Identify.
Rubidium.
Rubidium?
Barium.
Barium? All right, well, let's first of all, before we start arguing about the element, how many are easy to remove? 2. Very good. So going from here to here, not a 400% increase. 3 times. From here to here, that's a big jump. That's a big jump. So 2 are easy to remove, right? So what column or group is it in? 2. So which one of these is in 2? Magnesium.
You did that on purpose.
I sure did.
Because you were going to put that second, and then you moved it because you knew that I was going to guess the second one.
Okay. So you always want to have your periodic table out when you're doing this.
Or always choose the second one, you know.
Wait.
It's like the SAT.
What? However many are easy, that's the column that it's in. For the A columns only, the representative elements. Alrighty. Do the 7s and 8s. And we'll have a quiz the next time we meet. Yes, Tom?